So today, I'd like to talk about the characterization of lenses, which is used in bidirectional transformations, and when its get and put functions are possibly partial. Before I talk about our studies, I'd like to introduce a notion of the bidirectional transformation and the lens. First, I would like to briefly explain the bidirectional transformation, referred as BX, with a specific example. So this table has the past 3 PEPM locations and the number of presented papers. As you can see, this table has an obvious mistake, but let me go forward and explain. From this table, we can extract a small table of PEPM locations for the past 2 years without the number of presented papers. Now, I fixed the mistake on this small table. I desire to fix the problem in the original table by making modifications only to the extracted table, because the original table may be too big in actual case, or other people may try to update the original table at the same time. And BX had a method to update the original table with differences in the extracted table. This method is called put, and this is one of the motivations of the BX. In BX, the process of obtaining of a small part of the data is called get. Also, we denote the original data as a source and the extracted data as a view. In the most of studies, S indicates the source and V indicates view. For the BX, Foster et al. Gave a novel approach, the lens. The lens is the pair of partial get and put functions. As I described before, the get function produces a view from the source. I think that's because it doesn't figure out. Oh, thank you. Thank you very much. The get function produces a view from the source. Yes. And the put function updates the original source with a modified view. However, we cannot define get and put functions arbitrarily because the get and put functions should be consistent. The most important consistency of the lens is well-behavedness. The well-behavedness is formed two properties, GetPut and PutGet. And these properties are called lens laws. Note that there are other lens laws, and we consider the other 5 laws later. GetPut states that the source is not updated if the view is not changed. This is GetPut. And PutGet states that an updated source find view generates the same view. Updated source generates the same view. These laws are also originally defined for partial functions by Foster et al. But these definitions you can see here are for total functions. For clarity, we use the circle symbol for the laws for total functions in our study, like these circle symbols. There's an interesting property about well-behaved lenses. Several put functions may exist for the get function, forming a well-behaved lens. But it is known that the get function that forms a well-behaved lens with the corresponding put is uniquely determined if it exists. This is an important property in our study. So let's move on to the characterization of the well-behaved lens. This map shows the implications of lens laws with other laws. For example, when the lens satisfies GetPut, the lens also satisfies source stability. Also, when the lens satisfies both source stability and view determinations, the lens satisfies put idempotency. These 5 laws in the right half are specifically defined on the put function. I will introduce them later. And let me add some yellow squares. The purple squares for lens laws for well-behavedness, and the yellow squares. Okay, yes. Okay, it's okay. When the put satisfies all the laws in one of the yellow boxes, all lens laws in the other yellow boxes are necessarily implied. In other words, these 2 yellow boxes are equivalent to each other. Fischer et al. Gave an interesting theorem. When put satisfies all lens laws in one of the yellow boxes, the put has the corresponding total get function that forms a well-head lens with the put. Also, the well-head lens satisfies all 7 lens laws in this map. Therefore, the yellow boxes and the purple box are the necessary and sufficient conditions for each other. Now I introduce the laws for source stability as an example of the other 5 laws. Source stability states that any source has a view update that does not change the original source when it is put. Fischer et al. Proved this theorem with the following statement. For the sake of clarity, we present all the laws in terms of total functions. Some programmers find it easier to define partial functions for certain problems, and our results can be adjusted to this setting. But is it true? Let me consider the case when get is a partial function. Let us assume that the conditions also follows for non-total functions. Obviously, a well-head lens satisfies source stability and the PutGet. From source stability, any source has a view that do not change the original source when it is put. Then from PutGet, any source produces a view. This is here. The get is defined on any arbitrary arguments. Defined on S. So we assume that the conditions holds for non-total functions, but this get cannot be partial. So this is a contradiction. This contradiction motivated our research, and our main purpose is to consider this problem. Furthermore, our study may be helpful in other ways. So there are some programming languages made for and used in BX. For example, Beagle is one of the languages and is implemented with the consideration that the original lens is defined for partial functions. Our study may help us to check whether these languages can express all well-head lengths or not, regardless of the totality. So in our paper, we aim to characterize lenses consisting of partial functions as Fischer et al. Did. Before the characterization, we define 5 lens laws for partial functions. After that, we characterize the partial lens in 2 cases. One in the case, only the put is partial, while a get is total. In this case, we show that the similar conditions given by Fischer et al. Hold. The other is the case where both get and put functions are partial. In the latter case, we show that the similar condition does not hold. Therefore, we introduce a new lens law and discover the new conditions with it. I'm going to divide the rest of my presentation into 4 parts: the definitions of lens laws for partial functions, the relations among lens laws with a partial put function, and then the characterization of lenses with partial get and put functions. I will conclude our paper at the end of my presentation. First of all, we have to define the lens laws for partial functions. GetPut and PutGet are originally defined for partial functions by Foster et al. Thus, we define the other 5 lens laws for partial functions for our study. These are the definitions for GetPut and PutGet given by Foster et al. The upper definitions are for total functions, and the lower for partial functions. You can see the down arrow symbol in the definitions for partial functions. This is the down arrow symbol. So this symbol means that if the left side is defined on the given arguments, it will be evaluated at the right side. For example, this get s down arrow v, means that if the get is defined on given arguments s, it will be evaluated to v. So this get is a possibly partial function. In the original definitions for partial functions, the functions are considered to account for the cases where functions are undefined on the given arguments. We defined 5 lens laws for partial functions. Source stability for partial functions is simply change the equal symbol in total to down arrow symbol. And view determination states that when some views are used in update arbitrarily source, if the update are successful and the updated source are the same, the views are also the same, regardless of general definitions and original sources. Put subjectivity states that any source S can be successfully obtained by the put of some pair of the source and view. And put injectivity requires to any source S that when S is successfully updated by some views and the updated results are the same, these views must be the same. These views must be the same. Put and impotency indicate that the source remains unchanged no matter how many times the source is successfully updated with the same view, these are the same views. Put and impotency is called put twice in other researches. We defined these 5 lens laws for our studies. Now, I would like to explain the implications among lens laws. I chose an example way to prove implications and characterization of lenses in the case only the put function is partial, while a get is total. Let me show an example proof of the implications of lens laws. The conjunction of source stability and view determination implies put idempotency. Please note that these 3 lens laws are defined only on the put functions. First of all, this is the definition of put idempotency. Our goal is to derive the consequent part of put idempotency from the assumption part of it, subject to the condition that a partial put satisfies both source stability and view determination. Thus, I begin from this term, the assumption part of the put idempotency. From source stability, any source must have the some views that do not update the source. Thus, we can add this. This term, the source S prime has a view prime, which do not update S prime. Next, the put also satisfies view determination. Since there's same S primes here and here, since there is the same S prime for the 2 terms, we can derive the equation V equals to V primes. Yes. By substituting V prime for V in this term, we can derive the consequent part of put idempotency. Finally, the implication is proved. I explained the way of considering the implications among lens laws, and there are other implications. Now I explain the characterization of the lens in the case only the put function is partial. This error is the implication just we proved. Also, GetPut implies source stability and it implies put subjectivity. Similarly, PutGet implies view determination and it implies put injectivity. In addition, the conjunction of put subjectivity and put idempotency implies source stability, and the conjunction of put idempotency and put injectivity implies view determination. And now let me add some boxes. The purple box indicates the laws for well-headedness. The yellow box is corresponding to the conditions given by Fischer et al. The yellow boxes are also equivalent to each other. When only the put function is partial, we obtain a similar condition as Fischer et al. Did. When the partial put satisfies all laws in one of the yellow boxes, the put has a corresponding total get function, forming a well-behaved lens with the put. However, what if we consider the case when both get and put functions are partial? This is the most important question in our study. Now, in this part, we consider the case both get and put functions are partial. To come to the point, we show that the similar condition given by Fischer et al. Does not hold. To remedy this problem, we introduced a new lens law and found a new condition with it. This is the same map I showed just now, but the implications from GetPut to source stability requires the get function to be total. Therefore, when we consider the case both get and put functions are partial, the similar conditions as Fischer et al. Does not hold. To remedy this problem, we introduce a new lens law named weak source stability. As the name implies, the new lens law is a weakened version of source stability. Source stability states that any source has a view update that do not change the original source. Yes, this is a source stability statement. In contrast, the new law weak source stability states the same conditions for particular sources that can be obtained by input on some source and view. We investigated the relations among this law. GetPut itself cannot directly imply the weak source stability, but it's possible to imply at the conjunction with PutGet. It means a well-head length satisfies weak source stability regardless of whether the get is total or not. The other implications are also shown. Add all other implications among them these laws. As before, let me add some boxes. The purple box indicates the laws for well-headedness. These yellow boxes are equivalent to each other. Also, these yellow boxes indicate conditions on the put. Similar to the theorem given by Fischer et al., we show that when the partial put function satisfies all laws in one of the yellow boxes, the put has a corresponding possibly partial get function forming a well-headed length with the put. I'd like to stress this theorem. This is the most important result of our study. Now, I conclude my presentation. These are major related works. The original definitions with partial get and put functions are given by Foster et al. The definitions of GetPut and PutGet are also given in their work. In our study, we followed a similar way to define the other 5 length laws. The conditions on the put to have the corresponding get is given by Fischer et al. This is the main question of our study. And we follow the way to characterize the length laws and illustrate the map implications among them as Nakano did. And let me talk about further work. We showed that the put idempotency and put injectivity are enough to form a well-headed length. The computational models for both idempotency and injective functions already exist. By combining them, the computational models for all well-headed lengths may be obtained. And this model may help us to check whether the programming languages used in BX can define all well-headed lengths or not. Another further work is to illustrate the bigger map, including other length laws. This figure indicates the implications among 12 length laws when both get and put functions are total, given by Nakano. And this is the map when only the put is partial. Some implications do not fall for this case. And this is the map when both get and put functions are partial. Certain length laws among certain length laws including weak source stability. Finally, I'd like to summarize the main findings of our study. First, we defined 5 laws for partial functions, and then we characterized the well-headed length with partial functions in 2 cases. One is the case only the put function is partial. In this case, we show that the similar conditions given by Fischer et al. Hold. The other is the case both get and put are partial. In this case, we show that the similar conditions does not hold. Therefore, we propose a new length law named weak source stability and prove new conditions with it. And thank you for your attention. This is the end of my presentation.
Thank you for the talk. Questions? Okay, well, actually, I do have a question. I'll start. Oh.
Thank you. Very nice talk. So because I also do research on BXs, so I actually have always encountered some similar questions from outsiders that I find very hard to answer myself. So I like to hear your opinions on it. I think one of the common questions is that the round-trip properties, the put, get, and get put laws are not enough to guarantee meaningful bidirectional programs because it only guarantees the condition where the view is not modified, and it says nothing when the view is actually modified. And so it's often requested that we add more stronger conditions to guarantee that the program we write are actually meaningful for practical purposes. So yeah, I like to hear your opinions on this.
So, honestly, I'm not so much familiar with all of whole BX because I just learned the lens laws for other laws implications. So, honestly, I've never heard such opinions that these laws are not so much strong. So,
okay. So I guess I can elaborate on maybe on this graph. So you see that yes. The PutGet law requires that the GetPut law requires that you are using the same V to put back.
Yes.
And you get an S prime which is equal to the original S.
Yeah.
But it says nothing when we have a delta V on that V. So we actually put a V prime and we get an S prime.
Yeah.
There should still be some guarantee on how different the new S prime with respect to the original S, right? So it's like if I perform some small edits on V, there should be a small edit on S. So I was wondering if you have ever explored this possibility of additional lens laws to characterize these additional properties.
Is this the strong GetPut, right? No? I remember that there's a strong GetPut as a lens laws. Sorry, honestly, I don't remember the correct definition of strong GetPut, but you mean does it? Did you mean that?
I'm not quite sure if it is enough for those concerns, but yeah. Okay, yeah, thank you.
Questions for Asma? Okay, I mean, this is a general question too, right? This is the well-known view update problems in database, right? So I wonder, I didn't follow most recently, what's the state of research in the database community on this?
Oh. So sorry, I couldn't.
Yeah, so the problem you're addressing in database is called a view update.
Yes.
Right? So they didn't study it, or how did they study these properties, these problems? Do they not have partial puts in database, right? Do they not have partial put?
Yes. So the reason why we consider the partial GetPut functions, right? You asked yes, right?
Yeah, so I'm just wondering. I mean, in database, do they have this problem, right? How do they address it?
So how do I say it? So I think that there may be a partial put for database because like this example. So if we change everything in the small table, so there's no updates to this table. So the put may be partial. So did you ask how to address the partial functions in the table database? Right?
Yeah.
How to address partial functions? So we consider before our study. So we consider there may exist a partial put in the database, but partial get is difficult to consider in the realistic database project. But like this studies, so partial get may not exist for real database, but so we consider the partial get and put function for this problem because there may be so to consider the computational models for get and put functions and verified lens. So in consider this problem, get and put may not be total. Some lenses may be partial to consider all verified lenses. So this is why and how to handle the partial functions, the problems.
Yeah, because they're arbitrary functions. So you can have the problem. And of course, for real application, they try to make it total and all that stuff. Okay.
I have a
I am closer, so I can answer some the part of the questions. Actually, as far as I know, SQL, even SQL is a Turing complete actually. So in that sense, it can be partial. So so it is one of the motivation in our research. Thank you for your question.
Thank you. Any more questions?
This is a question related to the question asked before.
Yes.
Why do you specify those two rules as the well-behaved lens? I mean, more generally, like
Generally,
is there any reason to pick those specific two rules, GetPut and PutGet, for the well-behavedness of lens?
so well-behaved is one of the we consider one of the most important consistency. I know that there are other consistency class questions, but lens laws like so I forget the names. Are very well-behaved or other laws. So, but the Fischer et al. Gave this theorem. So like this theorem. So we consider this problem because this is why we consider these problems. So, is it correct answer?
So is it basically because Fischer considered those two pair as a well-behavedness of lens?
Yes.
Uh-huh.
Fischer gave this theorem, and we consider this.
Another related question is that do you consider any other ways of lens-like families, like when the get is non-deterministic, like get or put is non-deterministic, so it gives you a different result, like it's not even a function. Do you ever consider that kind of related family of lenses?
Related families of lens laws. So other 5 laws. So other lens laws.
Yeah, I mean other lens-related types.
Other related types. So we consider just a symmetric lens, and I think that we consider the most basic lenses, and we didn't consider other lenses. Just we consider these lens laws.
Okay, yeah, that's a very hard question, right? Non-deterministic. So, yeah, okay, let's thank the speaker again.